Hi everyone, we are Team 2 from the Artemis Geology and Prototype Tools for NASA Return Missions team, and our members include Deivanai Palaniappan, Bobby Bress, and Allison Huang. Our project focuses on designing and prototyping a tool and container to securely transport and handle lunar samples for the Artemis missions.
So, our main objective was to design a container that will transport lunar samples back to Earth. These lunar samples include rocks, regolith, dirt from the moon, and it has to be all contained so that it can go back to Earth. And also, we had to design a tool that could open and close this container to make sure that these samples would not become contaminated and they could be safely transported back to Earth. In preparation for these, we first completed Earth Science modules which NASA provided us. This included videos with quizzes and slideshows we had to make so that we could learn a lot about NASA's work so that we could be more effective interns. We learned to use 3D designing softwares. These included Front Panel Designer, Tinkercad, and Fusion 360. All of these helped immensely in helping us accomplish our task. And we also had to review the Apollo Tools Catalog. This was a catalog made in the 60s and 70s when NASA was going to the moon through their Apollo missions, where it outlines all the containers and tools they used in order to collect and contain the moon samples so that they could be effectively brought back to Earth. This helped give us ideas for what we wanted to do and helped inspire our design. Our goals for this project was to collaborate effectively with our team online, as especially for 3D designing, it isn't easy when you're not in the same room as each other, so we had to figure out how to do that effectively. We need to learn to use 3D design software, the ones that we listed above. We had to understand lunar sample handling so we could more effectively contain the lunar samples so that they would not become contaminated and could be brought back to Earth.
To make our prototype, we began with a rough sketch of our design, focusing on the essential features needed to safely hold and transport the lunar samples. From this initial sketch and preliminary dimensions, we used calculations shown on the right to estimate the dimensions of the container. We utilized the density formula and kept in mind that the density of most lunar regolith is about 1.5 grams per centimeters cubed. Ensuring their design could hold up to 10 grams of lunar regolith was a key requirement of our project. The density and abrasive nature of lunar regolith were also carefully considered during this phase to ensure the container's durability and capacity. Next, we moved on to 3D prototyping, utilizing Autodesk Fusion 360 for several critical elements of the design. We created a hinge and latch system to ensure that the box could be securely opened and closed. The hinge system was modeled to withstand the harsh conditions of lunar transport. Additionally, we created a joint modeling system in Fusion 360 to test the box's structural integrity and functionality. To further refine the opening and closing mechanism, we used Tinkercad to integrate the tool design and the rings seen on the lid to facilitate easy access while maintaining the sealing. This involved creating a precise and user-friendly mechanism that allows for the safe and efficient retrieval of the samples. Our container is designed to hold a maximum of 10 grams of lunar sample, considering the sample's weight and the need for secure containment. We kept in mind the fact that the container should provide an airtight seal to prevent any contamination and preserve the lunar samples for future scientific analysis. This airtight sealing is critical to prevent exposure to the Earth's atmosphere, which could alter the sample's properties.
Okay, as for the results, our design did work as intended, but it could be modified for ease of use. The hinge was slightly too large and didn't fit from the lid to the container. Our future plan is to optimize the container dimensions to ensure a perfect fit with the lid. The hole that we used to open the container didn't fit correctly, and in the future we may reprint it with a stronger filament material. We'll also resize the hole and the thickness of the tool used to open the container so that it's better supported. And more of our future steps, we will finalize the container and tool design for a perfect fit, and we will reduce unnecessary space to make the container airtight. As for choosing the material used for the box, NASA uses 3 main materials stainless steel, anodized aluminum, and Teflon. And we decided to choose anodized aluminum to reinforce the box's structural integrity.
Here we have a variety of images of our design and our product. In the top left, that is a design that we made in Fusion 360 that shows the dimensions and from a variety of different angles. Below it, you can see a design of the tool also from Fusion 360. And to the right of that, you can see the box in Tinkercad where the lid is attached. But upon printing, the lid and the container are printed separately as the lid is meant to attach through the hinges onto the container. Our first attempt, as you can see with the green box in the bottom left of the right, the hinge didn't exactly fit in right, and we believe this was an error in the printing, as we used a different printer, and on the black box, as you can see on the top right picture, it fit much better onto the container. Through the black box, you can also see the hook tool, which on the bottom right shows how the hook can go into the hole to open and close the container to make it so that it can transport the lunar samples.
We'd like to thank the following people for this amazing opportunity. We'd like to thank Margaret Baggio and Selena Miller for making this all possible. We'd also like to thank our mentors, Maritza, Montoya, and Suzanne Foxworth, for their invaluable guidance and assistance throughout this whole process. Finally, we're grateful to all the NASA Ares speakers, the SEA speakers, and the University of Texas Center for Space Research for giving us this incredible opportunity to contribute to the Artemis missions.
Some of the highlights for this program: the SEAS program has allowed us to learn how to work collaboratively in a scientific setting, and one of the best features of this internship was the guest speaker sessions. We really enjoyed hearing from industry experts and NASA engineers who shared their experiences and expertise. One of our biggest challenges that we had to face was communicating effectively online. The 3D design software we used wasn't collaborative, so it was difficult to adapt our designs. I'm Allison, and I gained a better understanding of what NASA engineers do and the skill sets needed in the field. I've also become more interested in pursuing a career in aerospace engineering.
My name is Deivanai, and my SEAS experience has enhanced my interest in STEM. It's motivated me to pursue a degree in aerospace engineering with the goal of contributing to future space exploration missions.
I'm Bobby, and SEAS has shown me a lot about how NASA runs and has taught me a great amount about different parts of the industry. Here you can see our poster where we go over a variety of what we've already gone over in the slideshow, like the abstract, the methodology, conclusion, etc. And as you can see on the right, there's more images, some of which we have shown, some of which we haven't, that show our design and our product.
Thank you so much for listening to our presentation. We appreciate your time and attention. Does anyone have any questions?